So today we're going to talk more systematically about stress. In the first lecture, we sort of used stress colloquially to talk about, the forces in the earth that arise due to tectonic motion, of course. Now you've all also had engineering mechanics, right? So you were introduced to stress, and you're probably introduced to it sort of like this, right? That stress is the force divided by an area, okay? And that if you look at that equation, it sort of implies that stress is a scalar, right? Force is like a number divided by a number is just a number, okay? But we also know force is really a vector. Remember in your statics class, that's all you did was a bunch of vector addition and subtraction and manipulation. So force is clearly a vector, right? So area is clearly a scalar. So if you have a force divided by, a vector divided by a scalar, you still have a vector, right? So stress is not a scalar, it's at least a vector, right? It just, in this case, it's still a vector, it's just all of the components but one are zero, so you can sort of describe it as a single number, a scalar, right? So we have some area, and we have some force on it, some force, okay, some area. And so stress is force divided by or normalized by some area. And it turns out if you take like graduate courses in continuum mechanics, you can realize that you can actually describe stress in terms of many different areas because, right, you have a body that's undeformed and then you squeeze it and it's deformed. Well, which area do you choose? You could choose to normalize it by the undeformed area, or you could choose to normalize it by the area that is after you deformed it, okay? And so we're not going to do that. We're going to assume that the deformations are small enough that there's just sort of one area, and it's sort of the reference configuration, okay? And but nevertheless, also, so the force divided by the area, and it's also a point-wise quantity. Stress is a point-wise quantity. So what I mean by that is that, mathematically a point is like something has zero volume, right? And clearly this bar, as I have it drawn, has a volume. So we would fill it with a whole bunch of points, in fact, an infinite number of them, right? So if I could draw these small enough and fill up the whole volume with those points, each of those points would have its own stress, okay? Now it turns out that because this is a uniform cross-section and I'm applying the force uniformly, while each of them would have their own stress, they would all be identical to each other in this case, okay, as I have it drawn. Okay, but I guess what I want to say here is that let's imagine that instead of the way I have it drawn there, the area I want to draw there, I want to take the same force and I want to normalize it by this area, like an area that's a cross-section of the bar at an angle. Right? So I've cut the bar in half, and instead of cutting it on a plane perpendicular, I cut it at an angle. And so now this area is different than that area. Everybody agree with that? Right? So the initial area was a circle, and then now this is like an ellipse because I've cut across at an angle. So the force is identical. The force is the same, but now I want to normalize it by a different area. So clearly, if I just use this equation, I'm going to get a different value, right? But I told you this bar is uniform. I'm pulling on it with the same force. The stress should be the same everywhere. So there's sort of a paradox here, right? Because I just have one equation, one force, two areas, I get two different answers, but we know the stress is the same. And so what it is that the stress is, first of all, not a scalar. It's a tensor. We'll talk about what a tensor is in a second, okay? But it's also dependent upon the coordinate system that you choose, right? So here, it's like I embedded a coordinate system, say, in this plane. And over here, I embedded a coordinate system in the plane of the cut. And it turns out that if I know the stress here, I can use a transformation. And in the linear algebra, we talked at least showed equations for how a matrix transforms, right? And it turns out, for the purposes of this class, the stress tensor will also be a matrix. That's not always true, okay? Not all tensors are matrices, but again, for the purposes of this class, the stress tensor we can treat mathematically like a 3x3 matrix. So we can transform it like a matrix. So in other words, if I knew the full stress, in either case, here or here, I can use a matrix transformation via basically essentially the transformation of this coordinate system to that one through the angles. Really, you can see that's just sort of a rotation of coordinate systems, right? So if I just rotate this coordinate system into that one, then I can transform the stress appropriately. And so therefore, we can see that they sort of mathematically all represent the same thing. It's just via a coordinate transformation, or it's dependent upon the coordinates that you choose. Okay. So So let's look at a piece of the crust of the Earth. I'm gonna cut out a little piece of the crust, okay? Now we know from what we talked about last time that there's stresses on this thing because the crust is moving around slowly, and it could be due to depending upon exactly which piece of the Earth we cut out. It could be near a divergent plate boundary where a magma is coming up and pushing this plate across away. It could be in a subduction region where one plate is moving under the other. All of those cause forces on the crust, squeeze it, right? And so let's draw some arbitrary forces on the crust, right? So this thing is being squeezed in some way. Turns out my drawing's not really realistic because almost all of the crust is in compression. Right? So these arrows imply that it might be in tension, but it doesn't really matter. So I guess just to be okay. So I have this piece of crust, and those forces that act on the outside, we're going to call those tractions, right? So these are tractions, and what tractions really are sort of stress vectors, right? So they have units of force per unit area, okay? But they also have a direction. So we call these tractions. It's like a stress vector. It's a force per area. All right. And then, of course, if we were to look at, say, any little infinitesimal cube inside this guy, so any little infinitesimal cube inside that guy, there's also going to be a body force acting on it. What's the body force? There's at least one. There could be more, but there's at least one body force acting on all of us. Gravity, right? That's a body force. So there could be other body forces. Electromagnetic forces are also body forces. But there's at least gravity for sure if we're talking about a piece of the Earth. And so I'm gonna take that little cube, take it, and I'm gonna pull it out over here, okay? And I'm gonna redraw it. And in fact, I'm going to redraw it on a coordinate system. And I'm the modeler, so I can choose the coordinate system. So the coordinate system is going to be, I'm going to label it x1, x2, x3. And so now I'm going to draw my little cube on that coordinate system. Okay. Now, because my big piece of crust has external forces on it, and my little cube in the middle there is also going to have external forces on it, right? These same forces are going to be applied internally to my little cube as well as any body force. So let's draw those. Let's draw those surface forces. They'll again be tractions. So let's see here. So I have a force on this face. I'm going to call it T. It's a vector. And I'm going to use a little superscript here to say that this is in the E2 direction. And what E2 is a normal vector that defines the normal to this face. Okay, so this is E2. Right? And likewise, there's an E1 and an E3. So these are just unit vectors. You might be more used to seeing it like I, J, and K, right? You know, so these are just normal vectors that point in this case, because my cube is superimposed perfectly on my axis, they point in the same direction as my coordinate axes. They just have unit magnitude, okay? And they define the faces of the cube, okay? And the reason I drew them on there because I want to say that this vector here, it's on the face defined by E2, but not in the direction of E2. You understand? So this, I mean, I clearly drew it that way, right? This guy is pointing in a different direction than that one. Okay? But I used the superscript E2 to say that it sort of emanates from the face that's defined by E2. Right? And likewise, we're going to have a T in the E3. Okay. Again, not in the E3 direction, but on the face E3. And a T in the E1. And my little cube is in equilibrium, right? It's not in motion. So if I had a cube and I pulled on three sides of it like that, and there were no counterbalancing force, the cube would fly through space, right? So my cube is in equilibrium, which means there's going to be equal and opposite forces on the back side of the cube, right? So the plot's going to get a little busy here, but you know, so like back here, there's a force that's equal and opposite to TE2. Down here, there's a force that's equal and opposite to TE3. And back here, there's a force that's equal and opposite to TE1. Okay? So I'm going to do one last thing with this plot. and that is I'm going to take my cube and I'm going to slice it on a diagonal. So I'm going to take this guy and I'm going to slice it like this, right along the diagonal. So if I take a cube and I slice it on the diagonal, what is left? Two geometric things. What are they called? They're sort of little pyramids, right? If I take a cube and I slice it along the diagonal, there you go, a tetrahedron. It was written there. Okay. And there it is, okay? So I cleaned it up. But all those vectors are exactly what I had just drawn for you. So we took this little cube out, and we labeled its faces, and then we just drew vectors on it, and this is what we have left, okay? Now, in mechanics, when you don't know anything else, where should you start? If you don't know anything else and you're trying to solve a mechanics problems, where should you start? Well, we have that. That's what we just did. This is a free body diagram. Force balance, okay? Another name for force balance is attributed to this guy Newton, right? Newton's second law, right? Or maybe more technically, conservation of linear momentum, right? Okay. So whenever you don't know anything else in mechanics, write down F equals ma and see what happens. Right? So that's what we're going to do. So this is our free body diagram. It's probably a little more complicated seemingly, right? But and as we move forward, just keep in mind, all we're going to do is use geometry and F equals ma, right? So, I guess there is one thing to point out in that. In this, when we sliced it, we summed those forces on the other side of this tetrahedron, and we now have a force on this that's normal to this face, and we're just going to call it Tn. Okay. So that's this red vector that's emanating from the front face that we sliced here, and it is labeled via or defined via the normal vector n. That's a normal vector to the face of that tetrahedron right there. Okay, so n, let's see. So n is a unit vector that has components n1, n2, n3. And what they are, they're the cosine defined between n1 and the x1 axis, or rather n and the x1 axis. N and the x1 axis, cosine of n with the x2 axis, and the cosine of n with the x3 axis. So I don't actually know what the angle is, right? But there's some angle between n and the x2 axis, between n and the x1 axis. So that's why I wrote it like that. But I don't know exactly what the angle is. And there's sort of one more preliminary thing. If we have if you know, like, let's say, if you have a line L and it has some angle theta, right, between that, some plane or some other line, there's an angle theta, then the projection of this line L onto this line, right, is what? So you know what I'm saying, the projection. So like this part of the line is what? Well, it's L cosine theta, right? Okay. So that same sort of rule holds if I have a plane, right? So if I take this line, and I extend it into a plane in space, right? And then I want to project that down. I want to project that down onto another plane, right, where the projection would be like this. Right, and the projected area would be down here. Everybody kind of see what I'm talking about in my drawing. I have imagine I have my plane here, makes some angle with the table, and I want to know what the area is sitting right under, right? So if I shined a light up here, I'd want to know what the shadow is underneath the page. So it turns out that we can use the same rule, right? So just like this is L cosine theta, if I know the area of this plane and I know that angle, so if the area up here is A and the area, then I want to know say what A prime is, which is the red area underneath, right? So I should probably use the right colors here. Right, so this is A, and this is A prime, then A prime is A cosine theta. Right. It's the same thing. Okay. So let's use the labels then. Let's use our free body diagram. So this is our free body diagram, and we're going to write F equals ma right here. Right. So these are tractions. Right. These little vectors are tractions, force per unit area. So in order to write F equals ma, force, I have to multiply by the area, right? So I have a force per unit area. I need to multiply by the area. Well, the area is dA of this face, and dA2, dA1, dA3. Right? So they're all drawn on there. So I'm just going to write F equals ma. Right? So I have Tn times dA. Right? So that's this guy. That vector times this area. Minus, because this is my positive coordinate systems are coming this way, so this is clearly going to have all positive components the way it's drawn. But all of these guys have negative components, right? The blue ones, they're in the negative direction. So minus T E1, and I want to write it in terms of, so I have dA1, but using our rule here, dA1 is in, right? It's the cosine of the angle. It's dA times the cosine of the angle between them, and the angle between them is the unit vector component, right? As we defined it up there. So then what I'm going to have is N1 dA. And likewise for the other components. So T, these are vectors. T E2 into dA minus T E3 N3 dA. Right, so that's the sum of the forces. Right? That's all forces. F equals MA. All right? So what's the mass of this thing? Well, the mass of anything is its density times its volume. Right? So I don't know if density is labeled on there, but we'll just use rho for density times the volume. What's the volume of a tetrahedron? What's the volume of a pyramid? 1/3 the area of the base times its height. Right? So that's why this little h is labeled here. So h is the distance between the centroid of this face and the origin. Or it's the height. You know, if I take that guy and I turn it over, I have a pyramid. H is the height. Right? So I'm going to have 1/3 h times the area of the base, which is dA. Right? So that's mass. Density times volume is mass. So that's m. And then A is just A. Newton's second law. Well, one thing we notice right away that there's a dA in every term, and so they can cancel, right? There's a dA in every term. All right, so the other thing is, you remember, and it was sort of the reason I wanted to make the point, that stress is a point-wise quantity, right? A point mathematically has 0 volume. So what we really want to do, if we're sort of trying to figure out what the stress is we want to take the limit of this as it goes to 0 volume, right? Or the limit is h goes to 0. Right? So if I shrink h, I shrink this tetrahedron to a point. So we're going to say, we're going to take the limit as h goes to 0, which you can clearly see makes this term go to 0, the whole term. So then the whole term goes to 0. Right? So what I have left is just over here. That is equal to 0. Okay? So I'm going to make a blank page and I'm going to rewrite this equation. Okay? Keep in mind, right, that these are vectors. Okay? So they have a little, I try to be explicit, they have a little vector mark over the top. So these are vectors. So while it just really looks like one equation, these of course have 3 components each. Right? So each t vector is made up of t1, t2, t3. Right? And so on the next page, I'm going to write out all the components. And really what this is, when you have a vector equation like that, you probably, if you've had linear algebra, you certainly have seen it, but even in your other classes, you can see that, you know, any times you have a system of equations, we can write them in a more compact form in like terms of vectors or sometimes matrices. Okay? So that's sort of what we have here is a system of equations, because each of these guys has 3 components, so we have 3 equations. All right? And so I'm going to write those 3 equations out on the next page. So what those 3 equations are T1 n T1 E1 N1 plus T2, sorry, T1, that's still T1. T1 E2. All right, so those are the three equations. And now we're just going to write them in matrix form, right? So this, in matrix form, is going to be T1 Everybody okay with that? Right. So that these three equations written in the matrix vector form are just like this. You know, you can see using your matrix vector row operations like we talked about. And if I just multiply this vector times the first row, I get the first equation. Right? And then multiply this vector times the second row, and I get that second equation. And the same for the third. So this thing right here is the stress. It's a tensor. Okay. Now, again, we're not going to really talk about what the differences are in this class, but really what makes a tensor is in the way that they transform via coordinate transformations. That's really all you need to know. Okay. So you can have basically, a vector is also a tensor. A vector is a first order tensor. What we have here is a second order tensor. And where they really, in terms of vectors and second order tensors, they're just, I mean, first order tensors and second order tensors are really just analogous to vectors and matrices, okay? It's when you go higher, when you go third order, fourth order, whatever, that's when you really see the differences, okay? But we're not going to do anything higher than the second order tensor in this class. So from now on going forward, we're just going to treat it like it's a matrix, a 3x3 matrix. Okay. Now, we often use, if you remember, right, what is the superscript, the E1, E2, E3? What did that represent on our original drawing? I made a big deal about showing you the difference between the vector and the unit vector. the face that the vector was coming from, right? So up here, the superscript is the face that the vector is coming from. Okay. The subscript is the component. Okay. The direction. All right. So it turns out it's not really that important. But I said this is the stress. This is actually the stress transposed. Don't worry about it too much. I'll fix it right here. Technically, this is the stress transposed. And the reason is, by convention, we're gonna instead of having subscripts and superscripts to describe everything, we're gonna use a new convention, okay? And that new convention, where now this is the real stress, has the components S11, S12, S13, S21, S22. Right. So if you really want to see what those are equal to, then it's like T1, E1, T1, E2, T1, 3, T2. And so this would help if you can remember what, I made a big deal that the superscript defined the face at which the vector emanated from, and then the subscript there was the component, right? The component of the vector, okay? So if you can remember that there and then you see this equivalence, then you can figure out what the shorthand here is. And the shorthand convention here is that the first number in the entry, what? Oh, yeah, I thought you hadn't heard that. The first number in the entry is the face, okay? First number is the face. And the second number is the component. Okay? So there's our stress tensor. I guess it's probably, in the mechanics literature, in almost every other field except geomechanics, it's typically the sigma is the conventional. Probably that's what you learned in engineering mechanics. You always use sigma for stress. In this class, you'll see S, okay? It'll be pretty much from here going forward, it'll be S, okay? So S is more common in geomechanics. And there's our, visual definition. Again, if you look at any face, then you have the three components. You'll notice that, again, it's the same as the convention that I just defined. This is the E2 face. So the first number is 2 in all those cases. That defines the face. The first number defines the face. The second, the direction, right? So the one direction is that way, the two direction is that way, the three direction is that way. And I have it in words here. So that is stress, mathematically. All right. Now, thankfully, there's a couple things. We're not going to go through it all, but what we wrote down was essentially, to get to this, we wrote down conservation of linear momentum, right? It turns out that we can use conservation of angular momentum to show that the stress, or at least this stress, which again technically is something called the Cauchy stress, named after the guy Cauchy that came up with it. The Cauchy stress is symmetric. The conservation of angular momentum leads to this conclusion, okay? So the Cauchy stress is symmetric. So now you notice that I've replaced, well, no, I didn't do it here, but I can replace, and you may see that going forward. But the only unique entries are above the diagonal, because S21 is equal to S12, S31 is equal to S13, and S32 is equal to S23. All right, so that's one thing that makes it easy, is that easier. We went from 9 entries down to 6 unique entries because of the symmetry. It just says what I wrote. And so yeah, there's the more collapsed stress tensor where I have the correct off-diagonal entries. And so it turns out that we can use it. Remember, in the sort of linear algebra lesson, we talked about matrix transformations. Okay, it turns out that if we have our tensor S, there is a particular matrix Q that will turn an S into a diagonal matrix. So a diagonal matrix is just one, it's all zeros and it has entries along the diagonal, right? So we're going to call that S prime. And it turns out that the particular matrix that does that is the matrix of eigenvectors. And we'll talk more next time about, it turns out that this S prime, the entries along the diagonal are the eigenvalues. So if you remember, I sort of introduced the eigenvalue problem, but we didn't. I said we'll come back to it when we're going to talk about stress. So this is what we'll do next time. We'll see that if we solve the eigenvalue problem and come up with the eigenvalues and eigenvectors, we'll see that the entries of S prime are the eigenvalues, and this particular matrix Q that can transform our stress tensor in this context into a diagonal stress tensor, those are called the eigenvectors. And they have to do with, essentially what you'll see is what we'll call them in terms of this is principal stresses and principal directions. Yeah?
Sorry, the values along the S prime are the eigenvalues?
Yes, yeah. More details next time, but yeah, essentially S prime is a diagonal matrix and the values along the diagonal are the eigenvalues. Okay? And we'll work an example next time, okay?